This happens to be a somewhat above average question. So let us read the question once appropriately. A body of mass m was slowly hauled up a hill by a force F which is always tangent to the surface. So this is the surface and the force F happens to be tangent to the surface always. So the trajectory of the mass is of course the trajectory of the hill itself or the shape of the hill itself. We are looking at a cross section. Find the work performed by this particular force if the height of the hill is given to be h. So this height is h and the base length of the hill is L. So here the coefficient of friction has been specified to be mu. We understand that the friction force is always going to oppose the motion. Friction always has a tendency to oppose relative motion between surfaces that are in contact with each other. So this particular friction force will also oppose the motion. The magnitude of the friction force is going to be equal to mu n. So this will be mu n, and this mu n is going to be equal to mu mg cos theta. Now the interesting part is the angle theta. We do not know the angle theta. So what we have to do in this particular question is construct an instantaneous triangle, if you will. So this is the instantaneous triangle that we need to construct, and this angle theta is varying, it's not constant. So this is the particular angle theta that keeps varying. Let us say this angle theta, this keeps varying. So this is an infinitesimally small triangle. It is important for the triangle to be infinitesimally small for me to be able to apply this instantaneous equation at every instant. So this happens to be dy and this happens to be dx, and the actual displacement ds, this is the actual displacement ds, which happens to be under root of dx square plus dy square in magnitude. So the work done, since it is hauled slowly, it is understood that the net change in kinetic energy is 0. So when the block was over here, it had 0 velocity, and when the block reaches over here, that at this point also it will have 0 velocity. So it is hauled slowly. That means the net change in kinetic energy is 0. This is to be understood based upon the statement of the question. So what we can write as the equation of the work done by the force F, the force of gravity, and the force mu n is as follows. The displacement instantaneously happens to be ds. So this yellow vector ds is the displacement. The net force is going to be nothing but F minus mu mg cos theta minus mg sin theta. So I again and again allude to the word theta-giri. So theta-giri means the understanding of how angles work in a particular free body diagram situation in physics. So according to theta-giri, this angle happens to be theta, and this normal reaction will be balancing out the mg cos theta component. So normal reaction is going to be equal to mg cos theta, and since the block is moving, we have to use kinetic friction, which is mu n, and which happens to be mu mg cos theta. So this is the net work, or rather this is the net force, and when I dot it with the displacement, I'll get the net work done. So the force is in the forward direction, and I have put minus signs already, so all these forces are assumed to be positive in the upward direction along the tangent to the trajectory. So if I just write ds over here now and cos 0, then I get dw. So this happens to be dw. Net work done is equal to change in kinetic energy. So if I just integrate dw, I'm going to get integration of f ds minus integration of mu mg cos theta ds minus integration of mg sin theta ds, and the net work happens to be net change in kinetic energy delta Ke. So this net change in kinetic energy happens to be 0 because the block is hauled slowly. So initially the velocity is 0 and finally also the velocity is 0. Thenceforth we get integration of f ds, and since the angle between f and ds is 0, integration of f dot ds is going to be just f ds. Okay, so we can treat this particular integration as if we are treating a scalar. Now this is going to be equal to integration of mu mg cos theta ds plus integration of mg sin theta ds. Now herein comes the interesting mathematical manipulation in the question. So this is equal to mu mg, and let us observe what is ds cos theta. So if we just scale this triangle up, then we understand that this happens to be ds, this is dx, and this is dy. So simply we can understand that since this is the displacement ds, this is ds, dx is going to be nothing but ds cos theta. So this is theta, and dy is going to be nothing but ds sin theta. So these are the two equations that we'll be using now. So this is mu mg integration of dx over here, which is ds cos theta, and plus so mg again is constant, so we can write down mg integration of sin theta ds. So that happens to be equal to dy. So I can write down that is equal to integration of dy. Now integration of dx happens to be the length L, and integration of dy happens to be the height h. So this I can thenceforth write as mu mg L plus mg h. So this is nothing but the work done by the force F which has been asked. Find the work performed by this force. So that is integration of f dot ds, and it turns out to be mu mg L plus mgh. So this is the work done by the force F, and that also happens to be our answer. This is our final answer.